Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky. The luminescent hearts of galaxies. Exploring Seyfert marvels. Seyfert galaxies are a subclass of active galactic nuclei, AGN, named after the American astronomer Carl Seyfert, who first identified them in 1943. These galaxies are characterized by their bright nuclei and the presence of strong emission lines in their spectra. Seyfert galaxies are among the most intriguing and extensively studied objects in modern astrophysics because they offer a glimpse into the dynamic processes occurring at the centers of galaxies, where supermassive black holes reside. Understanding Seyfert galaxies involves delving into the nature of AGN, the mechanisms powering their extraordinary luminosity, and the role they play in the evolution of galaxies. Seyfert galaxies are divided into two main types, Type 1 and Type 2. The primary distinction between these two types lies in the characteristics of their emission lines and the amount of obscuration of their central regions. Type 1 Seyfert galaxies display both narrow and broad emission lines, indicating that we can see both the narrow line region, NLR, and the broad line region, BLR, near the central black hole. Type 2 Seyfert galaxies, on the other hand, exhibit only narrow emission lines, suggesting that their broad line regions are obscured by a dusty torus of material surrounding the black hole. This dichotomy is explained by the unification model of AGN, which posits that the difference between Type 1 and Type 2 Seyfert galaxies is primarily due to the orientation of the galaxy relative to our line of sight. The central engine of Seyfert galaxies, like other AGN, is a supermassive black hole with a mass ranging from millions to billions of times that of the Sun. This black hole is surrounded by an accretion disk of infalling gas and dust. As material from the accretion disk spirals inward, it is heated to extremely high temperatures, emitting vast amounts of radiation across the electromagnetic spectrum. This radiation ionizes the surrounding gas, producing the characteristic emission lines observed in the spectra of Seyfert galaxies. The energy output of Seyfert galaxies can outshine the combined light of all the stars in the host galaxy, making them some of the most luminous objects in the universe. The study of Seyfert galaxies has provided critical insights into the physical processes occurring in the vicinity of supermassive black holes. One of the key tools for investigating these processes is spectroscopy, which allows astronomers to analyze the light emitted by Seyfert galaxies in detail. The emission lines in Seyfert spectra are produced by the ionization of various elements, such as hydrogen, helium, oxygen, and nitrogen, and their widths and strengths provide information about the velocity, density, and temperature of the emitting gas. The broad emission lines observed in Type 1 Seyfert galaxies are particularly valuable for probing the dynamics of the gas close to the black hole, revealing velocities of thousands of kilometers per second. The variability of Seyfert galaxies is another area of active research. Seyfert galaxies exhibit variability on timescales ranging from hours to years, which can provide clues about the size and structure of the emitting regions. For example, rapid variations in the brightness of the nucleus suggest that the emission originates from a very compact region, consistent with the size of the accretion disk around the black hole. Monitoring the variability of Seyfert galaxies over time allows astronomers to map the inner regions of the AGN and study the response of the emission lines to changes in the continuum emission, a technique known as reverberation mapping. Seyfert galaxies are also significant for understanding the interaction between supermassive black holes and their host galaxies. The energy released by the AGN can have a profound impact on the surrounding environment, a process known as AGN feedback. This feedback can regulate the growth of the black hole and influence star formation in the host galaxy. For instance, the outflows and jets generated by the AGN can drive gas out of the galaxy, quenching star formation and altering the galaxy's evolution. Conversely, AGN-driven shocks and turbulence can compress gas clouds, potentially triggering new episodes of star formation. The host galaxies of Seyfert AGN are typically spiral galaxies, although Seyfert activity has also been observed in elliptical galaxies. Studying the host galaxies of Seyfert AGN can provide insights into the conditions that trigger and sustain AGN activity. For example, interactions and mergers with other galaxies can funnel gas into the central regions, fueling the accretion onto the black hole and igniting the AGN. High-resolution imaging and spectroscopy of Seyfert host galaxies have revealed complex structures, such as bars, rings, and tidal features, which can be associated with such interactions. Multi-wavelength observations are crucial for understanding Seyfert galaxies. While optical spectroscopy provides detailed information about the emission lines, observations at other wavelengths, such as radio, infrared, ultraviolet, and X-rays, offer complementary insights into the different components of the AGN. For example, radio observations can reveal the presence of jets and outflows. Infrared observations can penetrate the dusty regions around the black hole, and X-ray observations can probe the high-energy processes occurring near the accretion disk. The combination of data from different wavelengths allows astronomers to construct a more complete picture of Seyfert galaxies and their central engines. One of the remarkable aspects of Seyfert galaxies is their cosmological significance. Because they are relatively nearby compared to quasars, Seyfert galaxies serve as excellent laboratories for studying the properties of AGN and the relationship between black holes and their host galaxies in the local universe. By comparing Seyfert galaxies with more distant AGN, astronomers can investigate how AGN activity evolves over cosmic time and the role of AGN in the growth of supermassive black holes and the formation of galaxies. The discovery and study of Seyfert galaxies have been instrumental in the development of the unified model of AGN. This model proposes that the different types of AGN, including Seyfert galaxies, quasars, and radio galaxies, are fundamentally the same objects viewed from different angles and obscured by different amounts of material. According to this model, the central engine of all AGN consists of a supermassive black hole surrounded by an accretion disk and a dusty torus. The orientation of the torus relative to our line of sight determines whether we observe broad or narrow emission lines and the extent to which the central regions are obscured. The future of Seyfert galaxy research holds exciting possibilities, with new telescopes and instruments poised to make significant contributions. The James Webb Space Telescope, JWST, set to launch soon, will provide unprecedented sensitivity and resolution in the infrared, allowing astronomers to study the dusty environments of Seyfert galaxies and their host galaxies in greater detail. The upcoming Extremely Large Telescope, ELT, will enable high-resolution spectroscopy of Seyfert galaxies, providing new insights into the dynamics and composition of the gas in the central regions. Additionally, advances in computational modeling and simulations will help to interpret the observations and understand the complex interactions between AGN and their host galaxies. In conclusion, Seyfert galaxies are a fascinating and essential subclass of AGN that provide critical insights into the nature of supermassive black holes, the processes occurring in their vicinity, and the relationship between AGN and their host galaxies. The study of Seyfert galaxies has advanced our understanding of the universe in numerous ways, from the precise measurement of black hole masses to the investigation of AGN feedback and the evolution of galaxies. As new observations and technologies continue to enhance our capabilities, Seyfert galaxies will undoubtedly remain at the forefront of astrophysical research, shedding light on some of the most profound questions about the cosmos.